All right, picking up where we got some microphone trouble yesterday. Line angle formulas. So this is called the line angle formula. It shows the zigzag in which the carbon atoms are represented. Now, this zigzag represents carbon atoms. Every end and corner is a carbon atom. So this would be C, 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 C. And then this is saturated, meaning it has as many hydrogens on it as it can. And if it wasn't saturated, we would see double bonds, and of course it wouldn't. It wouldn't have a zigzag shape in real life. This is a tetrahedral sort of shape here. And so what we would do is we would just fill in the number of hydrogens that we know each carbon can still have. So each carbon on the ends only has one bond to the other carbon, so it still has room for 3 more hydrogens. Every internal carbon already has 2 bonds to other carbons, so it can only have 2 hydrogens. So this is the line angle formula. Now, when we try drawing these, we can draw the expanded, the condensed, and the line angle all together. So you would first look at the name, figure out how many carbons that is. Pentane is 5, so we would do 5 like that. With the expanded, we want to show all bonds to hydrogens. The tedious part here. For the condensed, you just take each of these groups and write them without showing the bonds. So this first carbon would be written as CH3 because it has 3 H's on it. CH2, 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 and then another CH3. For the line angle, every end and corner is a carbon, and so as long as you only have 5 of those, you've got pentane. Let's talk about some conformations of alkanes. Now, carbon atoms in a chain are connected by CC bonds. Now, these CC bonds can rotate. There's rotation around them. If you play with the model kit and you use the rotate function, you can see that, that these bonds, if you build a model, if you had models to actually use in person, you could see this rotation as well. To give you an idea of what I'm talking about here, let's say that, well, actually I have a slide, but we can end up with different arrangements, and here is that sort of view. So here's butane. Butane has 4 carbons. You can see the condensed structure here. If I were to rotate this bond down so that the groupings of these 2 remaining CH2, CH3s was just down, that would kind of turn into this structure here. You can see that the way that we draw butane can actually widely vary. Drawing it up and down like this is not different than left to right. Having it make a kind of U shape is not different than having it make an L shape. What we care about is the connectivity, how they're connected, not what way we draw them. So sometimes students struggle with that part of organic chemistry, being able to look at a structure and know if it's the same structure or a different structure. So you should be looking at these and seeing that these are all the same structure. These are not isomers, and we're going to talk about isomers in a few minutes. Now, what I was trying to show is that if I had a CH3 and then another carbon, I'm going to expand this for a minute. Let's do some dashes. So let's say that my carbon here had 3 groups. It was a chlorine and then 2 other hydrogens, one coming out at us and one going back into the board. If I rotate around this axis, the CH3 would be held constant. The carbon would just turn so that, let's see if I'm rotating it this way, the one that is pointing out at us, the hydrogen, now that would be pointing back. the hydrogen that was pointing back would now be pointing out, and the chlorine that was pointing out would now be pointing towards us. Everything would rotate like this. And this can continue to rotate. In fact, it's in real life, it spins so fast like a propeller blade or like a fan. You wouldn't actually see the atoms, it'd just be a blur of them. And so free rotation is what's responsible for all of these different conformations. Now let's talk about cycloalkanes. These are cyclic. They have 2 fewer hydrogens than an open chain form, and that's because in order to get this carbon to connect to this carbon, we have to lose one of these bonds on each of these carbons. So the general formula for these, and I don't know if I've given you the formula yet for alkanes, but for an alkane, we can predict how many carbons and hydrogens they'll have. Whatever the number of carbons, it's just twice that number of hydrogens plus 2 more. And that's for alkanes. So cyclic alkanes would not have that same formula. And all you would have to do is just check the formula to know. If I gave you C3H6, which is the formula of this cyclopropane here. Propane because it's 3 carbons. Cyclo because it's a ring. That's actually how we name cyclic compounds. We put the word cyclo in front and then name the carbon chain exactly how we would have named it, just based on the number of carbons. But looking at the formula, C3H6, we see that it doesn't fit the rule for alkanes. So we would know right off the bat that wasn't an alkane. Now, we wouldn't necessarily know it was a cyclic compound because something we haven't looked at yet that we will in this lecture is alkenes. And alkenes also have the formula where you're missing 2 hydrogens. So if we have this sort of formula, it could be an alkene or a cyclic compound. Here are some more cyclic alkanes, just so that you can see the next couple of, well, of course, you have to have at least 3 carbon atoms to make a ring. 2 carbon atoms is just a line. So so starting with propane, then cyclobutane, cyclopentane, cyclohexane. Cyclooctane would look like a stop sign. Cyclodecane has 10 sides, and so on. We could also name these with substituents. I don't know if I have an example of that. If we were naming a cyclic compound with a substituent on it, in fact, we'll do an example here. So first you try to do these. So pause it, name these. Give it a shot. Hopefully you would have counted this line angle correctly to see that there was 8 carbons, therefore octane. Hopefully you noticed that the corners in this cyclic compound that numbered to 5, which would have been cyclopentane. Now, let's say that there was a methyl on here, a CH3. Well, this still would have been cyclopentane. Just like if we were naming a regular pentane, we would have to indicate that this has a methyl on it. So this would be methyl cyclopentane. Now, we don't have to say 1, 2, 3 or anything like that, because doesn't matter where we number, whatever the group is, or wherever the group is, we could just call that carbon the number 1 carbon. If there happen to be 2 groups, then we could give priority or number in a way that would give the lowest number to all of our groups. For example, if I had another group here, let's call it another methyl, numbering in this direction would give me 1 and 5 dimethyl. But numbering in this direction would give me 1, 2 dimethyl. So you'll always try to number in a way that will give you the lowest number. Okay. Another quick learning check. Try to do these. So hopefully you are getting more comfortable with the condensed structures and the line angle structures. So butane, cyclopropane, octane, and cyclohexane. Okay, alkanes with substituents. So we haven't named many alkanes with substituents yet. So I just gave you an example there with with a cyclic compound, but we'll do it now with some structural isomers and some substituents on regular chain. Well, you're going to see that structural isomers are the evolution of basically having alkanes with substituents. So the learning objective in this section of the chapter is to write the IUPAC name for alkanes with substituents and to be able to draw their condensed structures and their line angle structures. Okay, just to point out here, the substituent that we're talking about is going to be this branch. Okay, so this is branches or functional groups, basically things other than carbon or hydrogen. So branches, functional groups, or atoms other than carbon or hydrogen. Both of these formulas are C4 because we see 4 black atoms in there. Using our n times 2 plus 2, we would know that there should be 10 hydrogens on here. And you'll notice that that is true about both of these formulas. Both of these compounds have the same formula, but they are arranged different. Instead of sticking that 4th carbon on the end of our growing chain, it's been stuck in the middle of a 3-carbon chain instead. So this has created a substituent, but it's also it's a segue into the idea of isomers. So keep that in mind. Both of these have the same formula. That makes them isomers. So structural isomers, they have the same formula. They have a different arrangement of atoms. They have the same number of atoms, as I showed you in that previous example. And so they have the same formula because they have the same number of atoms. But they are different in most other aspects. Other than their same formula, they have different boiling points, different melting points, different appearances even. All right. So butane has 2 structural isomers. There's only 2 ways to connect 4 carbon atoms with a bunch of hydrogens. As we start to get more and more complicated molecules, meaning as we start to add more and more atoms to our compounds, so pentane and then hexane and then heptane, we have the opportunity to actually draw even more isomers. So butane only has 2. Let's see if you guys can figure out how many isomers pentane has. All right. Trying to remember how far I need to go with the recording here. I think that's about it. Okay, so that should get you back to video 1 where the microphone is now working. Okay, so I'm going to jump ahead back to where video 2 should be starting off with alkenes and alkynes. All right. Oops. Went a little bit too far. There we go. Now, alkenes and alkynes. So ethene. Ethene is what's being sort of depicted here. So, well, it's actually not being depicted, but those are bananas. I'm sure you could tell those are bananas. C2H4 is ethene. Now, it's not ethane. I didn't spell it wrong. Notice that our alkanes have now become alkenes or alkynes. Okay? Different spelling. They indicate a different number of bonds between our carbons. So where all of our alkanes had 1 bond between atoms, our alkenes are going to have 2, and our alkynes are going to have a triple bond. So ethene here, C2H4, more commonly known as ethylene. Actually, I can't spell ethylene. Ethylene. Sorry about that. It's an important plant hormone. that's involved in the promoting of ripening of fruits such as bananas. So that's why I'm showing it here. So the goal in this chapter is going to be to write the IUPAC names and to draw the condensed structural and line angle formulas for the alkenes and alkynes. So alkenes and alkynes are a family of hydrocarbons that contains double bonds. I guess double bonds and triple bonds respectively. So double bonds for the alkenes, triple bonds for the alkynes. They're also called unsaturated hydrocarbons. They're called unsaturated hydrocarbons because they do not contain the maximum number of hydrogens. How do I write that? Do not contain maximum number of hydrogens. They react with hydrogen gas to actually increase the number of hydrogen atom and to become alkanes. So that's one of the other things about these alkenes and alkynes is that they're reactive with hydrogen gas. Reactive in H2 to become alkanes. We call this reduction. And I guess more technically we call this hydrogenation. When something is hydrogenated, we reduce the double bonds or we get rid of the double bonds and turn them back into single bonds. And this has a lot of effects in some of the products that we use, such as oils and semi-solids. If we reduce those bonds, we can turn oils into solids. So peanut oil, for example, can be turned into a more solid peanut butter, or vegetable oil could be turned into a more solid type of margarine or spread. And so hydrogenation, we'll talk about how that actually works, but that's what it means, and that's what's actually reacting, is alkenes and alkynes are actually undergoing that when we make things like margarine or peanut butter. But we'll talk about the specifics of that down the road. So for now, let's just focus on what these double and triple bonds look like. So how do we identify alkenes? So alkenes contain one or more carbon-carbon double bonds, and I've illustrated it here in a ball and stick model as well as in an expanded model. So you can see here an expanded model, we're actually going to show the double bond, and that creates this bond angle of 120 degrees, which is different from the 109.5 that we had. So we don't get a zigzag so much anymore with these molecules, or at least not the same kind of angled zigzag. Okay, so in ethene, the two carbons are attached by that double bond. Now, this gives it a trigonal planar arrangement, meaning that it's flat. So if we were to turn it on its side, everything would be lining up in the same plane. And I encourage you to draw this molecule in that model kit and to take a look at that yourselves. Turn it around and see how it's flat. One of the other things that comes from this, and we'll discuss this more in a few slides, is that the double bond prohibits any kind of rotation around that bond. So where we had rotation around single bonds, we do not have that rotation around the double bonds, or the double bonds. So ethene, let's talk about ethene again. As I mentioned, it's commonly known as ethylene. Let me spell it correctly this time. Wow. Let me try that a third time. Slowly. There we go. Ethylene. It's an important plant hormone. I mentioned that. It helps bananas ripen. It also accelerates the breakdown of cellulose in plants, which causes the flowers to wilt and leaves to fall off of trees and that sort of thing. So it gets made, in the fall as a way of helping plants or flowers, not necessarily in the fall, but helps to lose those leaves or flowers. It promotes the breakdown of cellulose. We'll talk about cellulose a lot later in this course in the biochemistry side. Let's talk about alkynes. So alkynes contain one or more carbon-carbon triple bonds, and you can see that shown here in the same sort of ball and stick and expanded models. The bond angle here that we end up with is 180 degrees, which means these guys lie in a straight line. So this is linear. In ethylene, 2 carbon atoms connected by a triple bond. Each carbon is also still bonded to 1 hydrogen. And yeah, build this model. Take a look at it in the model kit. It's pretty cool. So alkynes have triple bonds. Alkenes have double bonds. Students often make the mistake of trying to draw line angle structures and then to go back in and put in a triple bond. Now, this hurts my eyes, but it doesn't, I understand what you're doing. As long as when you're doing your condensed structures, you don't still call this CH2 and then do, CH2. That's too many bonds to this carbon, right? This carbon has 6 bonds at that point. Real line angle structures can kind of be funny because they're supposed to be linear, right? Which means that these atoms here would all lie in a straight line because of the linear orientation, and then they could go back to doing their zigzagging. Condensed structural formulas for these obviously don't have any hydrogens on them, because each carbon already has 3 bonds in one direction. It can only have one other bond, and that has to be connecting to the other carbon, so no hydrogens. That should help a little bit. All right, give this one a shot. Pause the video. Try to identify these simply as an alkene or an alkyne, or if they're an alkane. We're going to worry about naming in a minute. All right, good. Double bond alkene, triple bond alkyne. If you were naming this, be careful to remember that that's 3 carbons right there, okay? Anyways. All right, so let's worry about naming alkanes, alkenes, and alkynes. So the IUPAC name for alkenes and alkynes is very similar to those for alkanes. We use the alkane name, same number of carbon atoms, and then we replace the ANE ending that we were giving them with an ENE or a YNE ending. So cyclic alkenes are named also just like the alkanes were. We named them as cycloalkenes. Did I say that? Cyclic alkenes are named as cycloalkenes. So you can see here ethane. If we were to introduce a double bond in there, it becomes ethene. If we introduce a triple bond, it becomes ethyne. Propane becomes propene, becomes propyne. Okay. For these, we don't have to specify where the double bond is, because there's only one place it could be. And even if I were to have drawn the double bond a different way, it's the same exact molecule, just reversed. It's just a turned around version. I'm looking at it from the other side, right? Same molecule. But as we get into bigger and bigger carbon chains, we're going to see that we actually do have to specify where our double bond is. Okay, so let's name these. So let's write the IUPAC names for them. So we'll start off by analyzing these structures and figuring out how many carbons they have, okay? So this one, A here, looks like it's a 1, 2, 3, 4, 5. So 5 carbon chain. So some kind of pentane. Now we see that there's a double bond in it, so I'm already going to write just pentene, because it's not a pentane, it's pentene. Now it also has, in this 5 carbon chain, a methyl group and a double bond. So we need to figure out, now there's different methods for figuring out how to name or where to start numbering. Since this is an alkene, we want our alkene, our double bond, to be on the lowest number possible. So in that sense, we're going to have to start numbering from this side so that we can get our alkene assigned to the number 2 carbon. It starts right here on the number 2 carbon and goes to the number 3 carbon. So this is going to be 2-pentene. Just to show you why I have to specify that this is 2-pentene, here's the same molecule, but the double bond is moved. Now, well, actually, this is still 2-pentene. But where A that we're drawing here is 4-methyl, right? 4-methyl, because the methyl group is on the number 4. This one that I've drawn over here would actually be 2-methyl 2-pentene. So we would actually number this direction. So maybe that was a bad example. Let me fix this so that it makes more sense for what I was trying to show you. So if I put the double bond here, this is now 1-pentene, because the double bond would be starting here on the 1 carbon instead of starting on the 2 carbon. So we have to specify where the double bond is. 1-pentene, 2-pentene, those are the different molecules that we can draw here. So 4-methyl 2-pentene, because the CH3 group, the methyl, is on the number 4. Let's see. 1, 2, 3, 4, 5, 6. So this is a hexane or a hexyne. We know it's a hexyne because there's a triple bond. It's on the number 2, so this is 2-hexyne, and it doesn't look like it has any substituents on it, so that's good. Now I did let this one have the worked out bits on it if you wanted to go over that on your own. Cycloalkanes, I mentioned that these are just cycloalkenes are cycloalkanes that have a double bond. They're named by assigning the double bond to between carbons 1 and 2. So no matter what kind of ring I have here, I guess this is I'll just do this. We're just going to pick 1 and 2. It really doesn't matter if you number it the other way, because I would just say that ring A is just ring B rotated around this direction, like if we just flipped it. So you can see that it's the same. It's the same. Shouldn't really matter what number or what carbon you pick, as long as you just make the double bond between number 1 and number 2. And that way it's already included in the name and it starts at number 1. We don't have to say that this is 1 hexene. Hexene. Not required to say 1 hexene. It's going to be implied. Sorry, cyclohexene. We don't have to say 1 cyclohexene. Now, it will matter when we are having other substituents, though. So if there is a Cl on here, well, then we do want to number in a way that's going to give that Cl the lower number. If I number this way, 1, 2, 3, 4, Cl is number 4. But if I number this direction, 1, 2, 3, 4, 5, then my Cl would be number 5, and we want the lowest number. So, again, those would still be accurate names for that compound. Anyone given that name would be able to draw this structure, but it isn't the best name, okay? The best name has our numbering for the one I've drawn here in red as 4-chloro-cyclohexene, because there's a double bond in there. Now let's name this guy down here. This is a 1, 2, 3, 4, 5 carbon ring. So this is a cyclopentane, but we know it's a pentene because we're talking about alkenes. Cyclopentene. Now, as far as numbering goes, again, we could call this 1, 2, 3, 4, 5, or we can number it like they did in red to get to our substituent. Here, the methyl sits on the 3. 3-methyl cyclopentene. So the carbon atoms in the ring are numbered to give, again, the double bond between 1 and 2, and then the lowest possible number to any substituent that you come across. Okay, these are on your own, so go ahead and pause it, give it a shot. Hopefully you came up with something close to cyclohexene and 3,3-dimethyl cyclopentene. You guys are already I'm hoping, impressing yourselves if you've named this, right? Ask, your parents or your neighbor or whoever you interact with on a regular basis to draw 3,3-dimethylcyclopentene, and they're going to think that you're a genius or something. And you kind of are, right? You're learning a new language here. This is the organic chemistry zone. I worked for a doctor at one point in my life who had gotten a C in organic chemistry when he was in his undergraduate. I don't remember he never actually told me what happened in med school, if that, affected him at all. But I remember thinking I was much cooler than him because I actually got an A in my OChem class. All right. Let's talk about cis and trans isomers. So carbon-carbon double bonds, I mentioned, don't rotate the way that single bonds do. The atoms or the groups of atoms attached to these carbon atoms on the double bond may actually form two different structures, which we call cis or trans. And so the learning goal here is just to be able to draw condensed structural formulas and to write the names for cis and trans isomers of alkenes. Cis means same. Trans means opposite or I guess on opposite sides. So same side, opposite side. So in this sense, if you were to think of your carbon or your hands as being carbon atoms connected by some double bonds here that do not rotate, right? No rotations. And your thumbs are some substituents that are sticking up. Well, these would be on the same side of the double bond. These would be cis. Now, if someone had a thumbs up and someone else had a thumbs down on the other side, then that would be opposite sides. Let me show you with some real molecules here. So again, in the alkene, the double bond is rigid and doesn't rotate. Groups are held in fixed positions. That gives these two isomers, that makes these two isomers possible. And so when we name them, it requires that we include the prefix, because if I tell you, well, I'll show you the molecule so you can see what I'm talking about. So if I were to give you 1,1-dichloro propene, okay, you can draw 1,1-dichloro, or actually, no, that's not right. Let me see what I was going to try to say was my example here. Okay, yeah. So if you have two groups that are on the same carbon, if they're both on 1,1, then we're not going to get any cis-trans isomers. We have to have groups on different carbons. And so first, just let's look at this, this first one. If they're on the same carbon, it doesn't matter what we're talking about. The rotation here doesn't matter because the two chlorines are on opposite sides of each other anyways. It has nothing to do with rotating. And even if we rotate this so that the CH3 was down, the Cls would still be on the same side, still be, so that is not something we look at. So the only time that when we do care about cis and trans is when the groups that are on the carbon atoms that are in this double bond are not both on the same carbon. So we'll take a look at this one, this butene here. So we've got two carbons that are locked in a double bond. Okay, same two carbons up here locked in a double bond. Carbon 1 and carbon 2, let's call them, even though that's not really carbon. Let's call them what they are. Carbon 2 and carbon 3. Carbon 2 and carbon 3, and this is also carbon 2 and carbon 3. Carbon 2 has carbon 1 up, and carbon 3 has carbon 1 up. Again, this bond cannot rotate. So these carbons, this is 4, and 4 is up, and 1 is up. They're on the same side. This creates a lot of, they're close to each other. This is a problem. This is called steric hindrance. There's a lot of repulsion here from these groups. This is a high energy configuration. The molecule doesn't like being like this, but it can't do anything about it. The bond doesn't rotate, so it's stuck like that. They're on the same side of the molecule as each other, so it's cis. And the other molecule we have here on the right, carbon 2 has carbon 1 down, and carbon 3 has carbon 4 up. That makes them opposite sides of each other. They're not influencing each other. They're not getting in each other's way. That's trans. They're on opposite sides. So when you're looking at molecules that have double bonds and you're looking at their carbons to see if they have substituents on them, you can now differentiate between them. So if I were to give you 2-butene as a name and to tell you to draw it, you could draw either one of these structures, right? In fact, you probably just would draw the line angle zigzag without realizing that you could actually draw this configuration as well. But now you know that there's actually two forms in that we don't have enough info here. We don't actually know which one we should be drawing. So that's why the name cis and trans is important. So in a cis isomer, the alkyl groups that are attached on the same side of the double bond, are attached on the same side of the double bond, and the hydrogens are on the other side. In the trans isomer, the groups and the hydrogen atoms are attached on the opposite sides. So you can see with the cis, the hydrogens are also on the same side, but in trans, the hydrogens are also flipped. So again, 1,2-dichloroethene could be drawn two different ways. And so if we really wanted someone to be able to know which one we're talking about, and why is that important? Well, they're melting points and boiling points and vapor pressures, and all of those are going to be different depending on which one we're talking about. So physical properties change differently with these two isomers. Again, in our bodies, when we worry about trans fats are worse than cis fats because the way that trans fats interact with each other is different. So now you guys know how to name these, hopefully, correctly. So let's see. When the prefix of cis or trans is placed in front of the alkene name, then you can identify which is which. So which one of these would get the cis name, which would get the trans name, right? So you'll start to recognize these just by looking at them, hopefully. Especially if I draw them properly. If somebody were to, let's see. Yeah, you guys will realize when you're drawing these, all of the different mistakes you can make when you're trying to represent cis. I'm having a hard time trying to show how people draw cis wrong because I've been trying to draw it correctly for so long. But I forget how easy it is to draw things just sort of randomly when you're new at this. So you guys are going to try to draw cis structures, but be drawing it more like trans, and it's not going to look right. Or you'll be like trying to draw down instead of, you'll have some weird little structures. But as long as you can identify them by, however you have to identify them. So what would the names of these guys be? So you still have to look for how many carbons you have. In this case, these are ethane or ethenes because it's a double bond. Do we have to say what number of carbon these are on? Looks like there's only 2 carbons, and so they're the only 2 that have the ability to double bond. We need to say where our bromos are, and there's 2. So we've got dibromo in here. Dibromoethene. Probably could have written that a little closer together. We've got dibromoethene, and then we've got them on either, the 1 or the 2. So 1,2 dibromoethene, where this guy is cis 1,2 dibromoethene, and this guy is trans 1,2 dibromoethene. All right, learning check. You guys do these. So use the name cis or trans where needed, but also do your best to name these, okay? I'll give you a hint. One of these is a dichloro, one's a dibromo, one's a dimethyl. Actually, that's not true. One is not a dimethyl. I lied about that. All right, go for it. So I was thinking this was dimethyl when I looked at it, but then I thought, that doesn't make any sense. It's just a 4-carbon chain. So that's butene, trans, because the 2 methyl groups are on opposite sides, as drawn. Dibromobutene here. This is basically the one we looked at in the previous example. And then a dichlorobutene, which is about the same. Bromos and chloros are pretty interchangeable. All right, good. All right, so let's talk about how some of these structures have a chemistry link to the environment component. So pheromones, for example, these are chemicals that insects and many other animals kind of emit, but I think most insects or many insects emit pheromones, and they're like chemical messages to other members of the same species, sometimes signaling that they're ready to mate, or maybe they're some kind of coordinating effort, or maybe they're even mimicry signals meant to cause a predator or prey to think that it's safe or to be turned off. So these things are pretty cool. Again, they warn of danger, they can mark a trail, they can attract the opposite sex, and they have to do with alkenes. So if you take a look here, this is bombicol. This is the sex attractant of this silkworm moth. The effectiveness of many of the pheromones that insects use actually depends on whether the cis or trans configuration exists in the molecule. So in this bombicol, it has one cis double bond and one trans double bond. And that has to have both of those for it to be effective. If it didn't have the cis and the trans, then it wouldn't do what it does. So it's very, very specific to the activity of the molecule. I thought that was really interesting. Okay, let's talk about reactions. This pretty much rounds up the end of the material. So we've done some naming. Now we gotta do some reactions. I mentioned the commercial process of hydrogenation. It's used to convert double bonds into single bonds. And we do this to turn oils into things like solids. So the learning goal here for this section is going to be to draw condensed and line angle formulas and write the names of organic products of these addition reactions of alkenes. So let's take a look. So alkenes and alkynes have double and triple bonds. Now these are very reactive and they undergo a few different types of reactions. They undergo hydrogenation, which is the addition of hydrogen gas in the presence of a catalyst, and it turns the alkene into an alkane. So where we have, I guess I can show you a little bit of if I have this, it becomes this. If we do the condensed structure so you can see, this is CH3, CH, CH, CH3. This becomes CH3, CH2, CH2, CH3. So it adds those two hydrogens, one hydrogen, to each carbon of the double bond. We can do hydration. This adds a water molecule. So similar to this example, we can add H2O or HOH. I like to write it as HOH so that you can see where the pieces are going to go. We call this hydration. And we can also add this to a triple bond as well, to an alkene, to an alkyne. So this one would give us an OH on one of these carbons. Of course, the other one would have that extra hydrogen that wasn't there before. So we're adding two hydrogens, or an H or an OH. And then under high pressure and temperature, we can also get polymerization to happen with double and triple bonds. And so I'll show you a little bit about the polymerization reactions as well. Okay, so let's take a look at these. What was I going to say? Oh, yeah, yeah, I completely forgot what I was going to say. Let's just go right into the reactions. Okay. Oh, I was going to mention these double and triple bonds. They're so reactive because they're easily broken. They are strong, but what you kind of get in Gen Chem is that there are certain types of high energy molecules that again, they're high energy because they've got a lot of strain in them, or they've got a lot of energy, kind of like a wound rubber band. That's what these are like. So they're easy to break because they want to break. They are not easy to break because they don't have a lot of energy in them. They do have a lot of energy. But we're talking about specifically alkenes and alkynes, not just triple and double bonds. Triple and double bonds in nature are actually more stable. When we see double bonded oxygen or triple bonded nitrogen, those things don't react. We're talking about carbon compounds here, okay? So organic double and triple bonds, they do break easily, and those electrons like to go to other molecules. Hydrogenation first. So in hydrogenation, the hydrogen atoms will add to the carbon atoms of the double or triple bond. If we had a triple bond, then we actually have to add 2 rounds of hydrogen gas, right? 1 round of hydrogen gas is only going to get us back to the alkene, and then the second round of hydrogen gas will get us back to the alkane. So to show that here, this is the alkene. This is the alkane. Here's the alkyne, and this would only get us to, again, the alkene with just 1 round. So we would have to do 2 rounds if we were starting with an alkyne. This is done over a platinum, palladium, or nickel catalyst. This often creates a surface for the electrons to move on and helps make this reaction go by faster. But at the end of the day, it reduces double bonds, and it turns unsaturated hydrocarbons into saturated hydrocarbons. Now, commercial this is really happening. Commercial hydrogenation is the cause of trans fat formations. And we'll talk about trans fats when we get to lipids later on in the semester. But that's what causes trans fats to form. Okay, learning check. Write the equation for the hydrogenation of 1-butene using a platinum catalyst. So pause the video, go and investigate what you think that means, give it your best guess, and then check the answer. This is what it's asking for. It wants you to draw 1-butene, to react it with hydrogen gas, to include the platinum catalyst. Usually that's shown over the arrow. I think that got moved out of the way. And then to show the product. So in this case, you were drawing 1-butene with the double bond, and you end up with just butane at the end. I like to ask, well, with this one, it wouldn't really be that same kind of answer because there's not much. What I'm trying to say is I might give you a product and ask you to draw the molecule that would have reduced to give me that product. So if I was like, here's butane, and it was the result of a hydrogenation reaction, what molecule, must have been the reactant? Well, there's actually quite a few options here, right? It could be that guy, it could be that guy. But I like to do that throughout the semester as well. So you should not only know how to name compounds, but when we talk about reactions, you should be able to do the reaction forward, but also be able to do a predictive, backwards reaction. Like what did the molecule have to look like before it turned into this, Again, with the hydrogenation, that might actually sound really easy because it is. That wouldn't be very challenging. But in the future with the hydration and then, amination and deamination, we can do a lot of different type reactions where that, reduction and oxidations, where knowing them forward and backwards would be more of a challenge. I was mentioning that vegetable oils are unsaturated fats, and they are composed of fatty acids that contain double bonds. And so by adding hydrogen to these double bonds, we make the solids. And so I'm just showing that here. So oleic acid, found in olive oil, has a double bond in it. Stearic acid, found in meats. Saturated fats does not have a double bond in it. So by hydrogenating, or even something called partial hydrogenation, we get rid of those double bonds. So, yep, that's how that happens. All right, you try to predict the products to these. So again, you're drawing the product, and test yourself with names as well. Try naming these reactants, try naming the products. So this first one is 2-butene. This first one is cyclopentene. Cyclopentene becomes cyclopentane. 2-butene just becomes butene. Hopefully these weren't too difficult. Let's talk about hydration reactions. So this is when water adds to the double bond, and it's asymmetrical because H adds to one side and OH adds to another side. So we end up with two products, right? Depending on which way you do it, right? We could get two different things. To illustrate that down here as well, we could get CH3, CH2, CH2, CHOH, right? Sorry, this would still be CH2. Is that too many H's? No. So what's the difference? Well, this one went on carbon number 2, and this one was on carbon number 1 in terms of where the OH went. So we need to figure out which way to do it. And there's actually a way. It's called Markovnikov addition. You don't have to learn that. But we can say it this way. The hydrogen is going to attach to the carbon that has the greater number of hydrogens on it. And the OH will go to the carbon that has the least number of hydrogens on it, or another way to say it is the more substituted carbon, the carbon that has more other non-hydrogen things. So when we take a look at the double bond here, we see already there is a carbon that has 2 hydrogens compared to 1. So if we had to figure out where our OH and our H are going, the H's want to be together. If we look at the other we look at the other carbon here, we see that that carbon only has 1 H, so again, that's one rule. Looking at this carbon, we see he only has one other carbon friend. But if we look at this carbon, we see that he has 2 carbon friends. He's more substituted. So that's where the OH is going to go. Now, anytime that we do this, we're going to end up with 2 products, a minor and a major. I'm only interested in the major products in this class. If you draw a minor product, I'll give you partial credit and tell you that it's a minor, because you won't know that it's the major because you didn't pay attention to Markovnikov addition. So that's your goal here, is to only draw the major product. Okay, so you need to remember the OH goes on the more substituted, or the carbon with the least number of hydrogens. Sometimes the major product is 75% versus 25. Sometimes it's 90% versus 10. Sometimes they're 50-50 products, okay? But in this case, Markovnikov addition does usually favor the major product here of the OH on that other least hydrogen carbon. Okay. Let's see. I think I had a practice actually for you. Oops. Let's try one. Unless I don't know what's happening here. My pen doesn't like me. Okay, I guess it's working. Let's see. Let me draw another one here. So, draw the product. Pause the video. I'm going to give you the answer in 2 seconds. There you go. We added the H and the OH. The H went with its friend that had, to the carbon that had more H's on it. The OH went to the carbon that had the least number of H's on it. All right, polymerization reactions. Let's talk about those. A polymer is a large molecule that consists of small repeating units called monomers. Many of these polymers are produced by addition reactions of alkenes. So we take alkenes and just let them react with each other to form big long chains. Now, In the last 100 years, the plastics industry has made synthetic polymers, such as those used in like carpeting, plastic wrap, non-stick pans, plastic cups, rain gear. You can see a few examples shown here. In medicine, even, synthetic polymers are used to replace diseased or damaged body parts, such as hip joints and pacemakers and teeth and heart valves and blood vessels. So polymers have a lot of importance. They're made up of monomers. In this case, you can see ethene or ethylene, as it's commonly known. So here's an ethene, here's another ethene, here's another ethene. And by letting them react, what happens is that this double bond just connects, instead of just being here, the electrons actually connect to these two carbons. So then we form a bond. And then that causes this carbon right here to have too many bonds, so then the double bond moves and connects over here. So now we have another bond. And we end up with chains, right? These are connected now ethenes, or commonly known ethylenes, so polyethylenes, polyethylene. So you've heard of it before. And polyethylene is one of the first, but is not one of the last polymers. Now, polymerization is made by taking many of these little monomers and adding them together, hence addition reactions. And you usually have to have high temp, you usually need a catalyst and some high pressure. And in these addition reactions, a polymer grows as long as each monomer is added to the end of the chain, and they can just keep growing and growing and growing. A polymer can actually contain as many as 1,000 monomers. And polyethylene, let's see, polyethylene is a polymer made from ethylene monomers. Ethylene. It's used in plastic bottles, film, plastic dinnerware. There's low density polyethylene and high density polyethylene. Low density is flexible, breakable, it's obviously less dense, and that's because it's more branched. So it has lots of branches. And then we have the high density polyethylene. This one is stronger and more dense, hence the word high density. It actually has it's less branched, but it has a much higher melting temperature as well. So, and that's from the branching. So the branching is what allows it to be dense or more dense. High density polyethylene is good for high temperature plastics. So it won't bend or mold in the heat like a low density one would. Here's a list of some of these guys, as you can see. Now, we have problems with plastics. They don't decompose very easily. Because these are alkanes, they're very unreactive. They're not biodegradable. They're pretty big contributors to pollution in land and on the oceans. We are trying to make them more biodegradable. You can see here that we are into recycling. Each type of polymer used has its own identifying recycle symbol, a little arrow. Like number 5 or the letters PP inside of the triangle actually indicate like polypropylene plastic, polypropylene, or chloroethene. They're all used for different scenes. Polyvinyl chloride, right? So vinyl chloride or chloroethane, used in like those like sprinkler pipes, and there's all kinds of stuff that PVC is used for. Polypropylene used in ski and hiking clothes, carpet, plastic bottles, medical face masks, tubing. Tetrafluorine, polytetrafluoroethylene is Teflon. 1,1-dichloroethene is saran wrap. Polystyrene, coffee cups, insulation. This is a short list. This doesn't have everything on it. So luckily we have lots of recycling programs to try to reduce the amount of plastic material that's ending up in landfills or out in the ocean, but work is being done to try to get microorganisms to break these things down for us. All right, aromatic compounds. I think this might be the last section. I thought it was reactions, but maybe it's this one. So let's look at benzene. Let's name some aromatic compounds and draw their line angle formulas. It was 1825. Michael Faraday isolated a hydrocarbon called benzene. It has 6 carbon rings. It's a 6-carbon ring, 6 carbon, with 6 hydrogens and alternating double bonds. You can see them here. So let's talk about. So benzene is what we call aromatic. And those come from a class of compounds that they give off smells, right? So this was first a ring of 6 carbons. It's a flat structure, and it's drawn with the 3 alternating double bonds, but it's represented by 2 structures because we can draw the double bonds alternating, but we can start on different carbons. In reality, the double bond is probably partial and all the way around, and so there's a hybrid structure that sort of has a circle shown in it. Anyway, so this is benzene, okay? So aromatic compound. Now most aromatic compounds are what we call conjugated. They have the ability to have these double bonds bounce around. Let me show you another one. Here is a octane, cyclooctane compound that also has a conjugated double bond system. So if this double bond moves here, this one moves here, this one moves here, and so we could just represent it with a circle. Aromatic compounds, here's a couple. Here's, we use these for flavor. Anisole, estragol, and thymol. These come from herbs. But again, it's the compound and the presence of this benzene ring that actually gives it these properties. Now, benzene, each carbon atom uses 3 valence electrons to bond to the hydrogen atom that it has and to the 2 adjacent carbon atoms. Okay? And so it has this additional 4th valence electron that was at first thought to be shared in the double bond with the adjacent carbon, but as it turns out that this double bond runs around. It actually is alternating between single and double bonds. And so that's what makes benzene kind of fun to study early on. This was like 1865 when they were figuring this stuff out. So benzene's really cool. It's been known for a while now. Aromatic compounds that contain benzene rings and have single substitutes or single substituents are called benzene derivatives. And you can see here that the ring only contains a benzene but one other thing on it. And some of the common ones are toluene. Toluene has a methyl group, also shown here, sticking out on the benzene. There's an amino, NH2, that we stick on a benzene, and we can call it aniline. And phenol is another common name for benzene with an OH on it, with a hydroxyl group or an alcohol functional group. We can also call these by their IUPAC names. So this would be methylbenzene, aminobenzene, or hydroxybenzene. But again, common names are often used. And some common names are even allowed by IUPAC rules. So in common names, when a benzene ring is a substituent, it's called phenyl. So here, this is the main compound, 1-butene, and on the number 3 carbon, there's a benzene as a substituent. We don't call benzenes benzyls like you might expect us to call them. Like a methane becomes a methyl, and an ethane's an ethyl. A benzene is not a benzyl. Benzyl is actually reserved for this guy. So if there was no bond here, a CH2 with a benzene all together as a substituent is called a benzyl. But when it's just the benzene group, we call it a phenyl. So don't let that name trip you up. When we have 2 or more substituents, the benzene ring is numbered to give the lowest numbers to all the substituents. It makes sense to automatically number something as a 1. You can see here then, you would number this way as opposed to this way to get the lower number. Here it doesn't matter, 1, 4. And on benzene, when there's 2 substituents, we can also use this other term. Instead of saying 1,2 dichlorobenzene, whenever they're next to each other like that, we call it ortho. So we would say that this is ortho dichlorobenzene. When they are in the 1,3 or one away from each other with a gap in the middle, we call that meta. So instead of saying 1,3 dichloro, you could just say meta dichloro. And when it's all the way on the other side of the ring, we call it para. I have this shirt that has this molecule on it. And it's a joke because it reads as paradox, para-D-O-X, because they're para. It's an OChem shirt, obviously, No, not everybody gets it. And it's not even really that funny because, yeah. But anyways, that's the shirt. So you can use ortho, meta, para in replacement of 1, 3, 1, 2, 1, 4, and so on. Let's see. What do I have this slide here for? When a common name such as toluene, actually that's what I was going to put here. When we have common names like toluene, phenol, or alanine, aniline, we can use those too. So like if I have, let's see. So let's say that I have this guy. So I can call this, 1 chloro, 2 methyl, alphabetically, right? 1 chloro, 2 methyl benzene, or I can name this as aniline, not aniline, toluene, and call this 2 chloro toluene. So whenever I name it as toluene, the methyl is automatically the number 1. If I had this guy, and this was, I can call this phenol. So automatically, if I'm using phenol instead of calling this hydroxybenzene, then phenol becomes the number 1, and this would be 3-bromo phenol. Or I could even say meta-bromophenol. Meta-bromophenol. I don't have to say that phenol is number 1 again because it's built into the name. Lastly, aniline, NH2. If I was calling this aniline, automatically that's the number 1. If I'm calling this benzene, that's not the case anymore. If I'm calling it benzene, then I have to number these guys just based on whoever's going to have priority. And it goes by molar mass. So whichever one of these is heavier, whichever adds to a bigger number, that would get the number 1. So just to be clear, if I was calling this middle molecule by its IUPAC name, this would be the number 1, and this would be the number 3. This would be 1-bromo, 3-hydroxybenzene. 1-bromo because bromo is bigger, but bromo's first because it's also alphabetically first. So a lot of rules. There are also common names like xylene for isomers of dimethylbenzene. So a lot of aromatic compounds have common names. You don't need to worry about these common names. If 3 or more substituents are attached to benzene, then they're numbered in the direction to give the lowest set of numbers and then named alphabetically. But again, these are just examples of xylene, which is just dimethylbenzene. And you can see orthoxylene just means they're next to each other. Paraxylene means they're across from each other, and so on. Toluene, very neat molecule. This is toluene here. You can see it in the parent chain. It's used to make, it's used as a reactant to make drugs and dyes and even explosives such as TNT. So here, 3 nitro groups have been added to this toluene. All right, trying to think of another toluene. I used to work on a molecule called DEET. It's a mosquito repellent at Fresno State. I did a lot of research on this. My thesis is on it. This is ortho-DEET, diethyl, because it's NN-diethyl toluene. So that's where the name comes from. NN-diethyl, the diethyl toluene is the DEET part. But I played around with all these different groups. I moved the methyl to different positions. I added CF3s and chlorines and bromines and all kinds of stuff. I even played with the length of these chains, and all in an attempt to either find a better, more effective mosquito repellent or just to figure out more about how molecules move around with the double bond. In the end, I graduated and got a nice paper out of it and a good grade, so I'm happy. Didn't end up learning anything though. My research is still ongoing. It's in someone else's hands now. Benzene rings are also found in pain relievers. You can see this here. This benzene ring aspirin and acetaminophen, and even in flavoring such as vanillin. So benzene rings are found in a lot of different biological structures, a lot of different organic compounds in general. And we'll look at a lot more when we get into the biochemistry side as well. All right, last but not least, let's take a look at some of these compounds here. So you give it a shot. Try to guess what the correct names are here. Hopefully you came up with those right answers. And that brings us to the end of the chapter. So good luck with this one. I'll see you guys during our meeting, and hopefully you guys don't have too many questions about this. I hope I did a decent job explaining it, but read the book, do the homework, do the practice, and that'll help. All right, see you guys in the next one.